It's always a pleasure to be here and to see so many new faces, and I won't say old faces, but longtime friends. Well, let's see. Last year, I described for you a model, a mathematical model of the Birkeland current, a cross-section of the Birkeland current, and what it looks like and how it counter-rotates inside, and how it manages to go from the sun to the Earth to Saturn and create the auroras on those planets. And I thought maybe this year we'd take a look at the other end, not the aurora, but the sun end, and talk a little bit about the solar wind. Because Birkeland, when he came up with the idea of what the auroras were caused by, said they were corpuscles, electrical corpuscles that were coming from the sun to the Earth. Of course, he was laughed at severely for that, but we now know that that is true. And astronomers, instead of calling it the Birkeland wind or giving him credit for it, they just call it the solar wind. So it's a bunch of essentially protons and electrons that come off the sun in steady state. Now, I'm not talking about, of course, CMEs, coronal mass ejections, or flares, or any of the transient phenomenon that happen, but the steady state, DC, as Ben would say, currents that are coming from the sun as a normal thing. One might ask why the solar wind is important, and I think that Ben has done a very good job of talking about why it's important that we know what's coming off of the sun. It's obviously a stream of charged particles that speeds up to about 1 million miles an hour. That's moving. And before it streams past the Earth. And disturbances in the solar wind pump energy into the Earth's radiation belts and polar regions. Space weather, clearly, as Ben points out, can change the orbits of satellites, shorten mission lifetimes, and create all sorts of havoc. The solar wind distorts the Earth's magnetic field and thus causes current surges in transmission lines, and pretty much we know this. So I'm not going to mention those things again. What I am going to talk about, I hope, for the first time, is some of the lesser known properties of the solar wind, and most importantly, how well those properties, those very subtle properties of the solar wind, fit in exactly with Ralph Juergens' electric sun model. And so, as I've said so many times before, you can't prove anything in science. You can disprove, but you can't prove it. But you can always add supporting evidence. You can build that wall, like the DA tries to build a wall of evidence that is insurmountable by the defense, and he says, no, he really killed him. This is what we're trying to do here, and that is to build that wall of evidence that says, you betcha, the sun is electric. We don't know whether it's powered completely by electricity. We think it might be, but we don't know. But one thing we know for certain, and that is that the effects, the major phenomenon that we see on the surface of the sun, those phenomena are electric. And I'd like to show you in some detail why I say that and what's going on. So there are actually two different types of solar winds. Perhaps some of you know that. And I'd like to explain the reasons why these properties are quite different from each other. The standard mainstream finds these observations to be, quote, enigmatic, as always. They're not enigmatic. They're very simple, elegantly simple. I'd like to explain how the different points of origin on the surface of the sun explain those differences between those two different types of solar wind that we see. One of the things, by the way, I should say that one of the things I want to show you is a short video clip that Monty Childs was kind enough to lend to me from the Sapphire Project that shows that the things that I'm talking about here, as far as Juergens' model is concerned are being repeated here on Earth in Monty's lab. So the Juergens sun model was proposed in the early 70s, and today I'm trying to propose a slight extension to that. And these proposals that I'm trying to make are based on Ralph Juergens' work, and also on something that I came up with and presented 3 or 4 years ago I called it the transistor model of the sun, because the sun, we'll talk about it in a minute, but the sun's surface works very analogously to the way a PNP transistor works. And we'll see that briefly at least. Anyway, again, to state the obvious, we all probably know that the major 3 layers on the sun that are important, and if you come toward the sun in the order in which you see them, would be the corona, the chromosphere, and the photosphere. Now, the corona is perhaps the most beautiful thing in the sky. It is this colorful. Those are, of course, the same colors that we see in the aurora. And why? Because it's the same thing. It is plasma in the glow mode. And it is the same sort of stuff, helium, hydrogen, mostly hydrogen, excited electrically. Again, everything I say, please ask yourself, while I'm saying it, how does the standard model explain this? The standard model has no explanation for why a corona exists in the first place. If the sun is just a nuclear furnace like a wood stove, my wood stove doesn't glow like that. And so clearly, everything that we observe around the surface of the sun, including the corona, is electrical in nature. One other comment, and that is that you can't see anything in the night sky that isn't plasma. Oh yeah, I can see the moon. Yeah, but of course the moon is reflected sunlight, and sunlight is plasma. The sun, where all of light that we see, if you look at Jupiter through a telescope, or Saturn, or any of the planets, you're seeing reflected plasma light. And we'll talk about the photosphere and where all that light comes from in a minute. But the corona is a pretty big thing. It extends out about 3 solar radii, if you look at half the width of that disk, and then do 1, 2, 3. It takes you out to about the corner of that picture, and you can see that's about the extent of the corona. So it's large. The sun is, 865,000 kilometers across, I think, something like that. The chromosphere, the second layer going in, contains these spicules. And spicules, we've all heard, the pines of Rome. The spicules are the fountains of the sun, not the fountains of Rome. But anyway, they have certain characteristics. Those spicules are really towering fountains of electrons that come up out of the sun and then back into the sun again immediately. If our assumption is correct, Juergens' assumption that the sun has a positive charge, those electrons, once spewed, are very quickly brought back into the sun again. And that's what the spicules are. The photosphere is where the action is, and that's what we're going to be talking about mostly. The photosphere consists of these things that the astronomers called photospheric granules. A more proper name for them is Anode Tufts. The anode tufts consist of plasma in the arc mode, and I've heard all sorts. Even one of my good friends thinks the sun is liquid hydrogen or something. It better be pretty hot liquid, because plasma in the arc mode puts out a horrific amount of power. And as a matter of fact, but I should say this, those granules come and go with time. They grow, they get bright, then they shrink and they go away. The power put out by the sun is really fantastic. That is to say, the radiation from the sun every square inch of the sun's surface, on average, puts out 42,000 watts. If you can think of what about a square mile, it's not boiling anything. It's arc mode plasma. The temperature of those granules or tufts is about 6,000 Kelvin, which is pretty, you wouldn't want to spend your summer vacation there, but it's in relation to the temperature of the lower corona, which is 2 million Kelvin. It's a medium temperature. Anyway, there's a picture of the granules. That's a movie. If you look at it very carefully, you can see it moving. It's a real-time motion picture of the granules. If you keep your eye on one, especially near I think that white stuff in the center is a bunch of spicules coming up through, I don't know, but I think that's what it is. And you see them, they're all over the place. Let's see. Yeah, where is it? There's some down here, there's some over here, up here, and of course a bunch of them here. If you keep your eyes on the granules themselves, you'll see them shrinking away to nothing. And the question is, why do they do that? Well, there's a typical sunspot. And you might say, well, what's a sunspot? Well, a sunspot's where the photospheric tufts are not. It's a region where the photospheric tufts don't exist. And so there's been a good deal of work done in the laboratory on anode tufts. And we'll talk some about that. The main focus, I would say, of Juergen's sun model is an anode tuft. How does the anode tuft work? And that's one of the things I'd like to spend some time on this morning. There is, of course, the penumbra. That's that orange ring that you can see. The dark inner area is called the umbra. And the temperatures in the umbra have been measured at, well, just something north of 3,000 Kelvin. So the umbra obviously is much cooler than the normal spots. I'm sorry, the normal tufts, which are the yellow region around the outside there. Anyway, I said that Monty had sent me some interesting pictures from Sapphire. There is one. Now, the purple wine glass in the back is not real. Monty has not been drinking. That's just an aberration of the photograph. This was taken inside a bell jar. And he and his team have managed to actually create anode tufts. The center bright purple thing is a spherical, although it's distorted some by the shape of the bell jar. It's pretty spherical, and it's the anode. And riding on top of that anode are anode tufts. And so the major property of these anode tufts is that they're made up of positive charges. And as such, you can think to yourself, just basic knowledge of electricity, if those things are each one a group of positive charges, then they don't like each other. They're going to be repelling each other. And so you see they're quite evenly spaced over the surface of the sphere. And as you'll see in a minute, when Monty increases the current, he increases the number of tufts and he increases the brightness of the tufts, and finally they turn into something in the arc mode, just like we see on the surface of the sun. So, as I said before, I think I said before, the main basis of the Juergen's model is an analysis of those tufts. And so we're going to be thinking of traveling in a line, if you can visualize, from the purple surface there, the surface of the anode, up through the tuft, and then out beyond the tuft. And let's think, what would we expect to see there? I'll tell you what Juergens expected to see there, and I think it's exactly what Monty is seeing and is going to see in his Sapphire experiment. Anyway, Juergen's electric sun model, and there it is. You've seen that picture many times. Every time I talk, I think I show it. It's fairly complicated, but let's take it one step at a time, and I think you can see what I'm saying. The upper one of the three graphs there is a plot. Well, all three of them. The horizontal axis is the radial distance up from the surface of the sun, up through the tuft and then out into the corona. The top graph plots the voltage that you would see if you had a voltmeter in your hand. You could have a ground someplace out in space and look at the voltage. How the voltage varies as you come up out of the sun, through the tuft, and then out the top of the tuft. On the left-hand margin, the left-hand axis there, the vertical axis, it's labeled energy per unit charge. That's volts. Energy, that's what voltage is. A positive charge has more energy if it's at a high voltage than as if it's at a low voltage. The analogy is that's the cross-section of a mountain. And the positive charge, the analogy there is a tennis ball. So suppose you threw a tennis ball on top of I'm sorry, wait a minute, I got ahead of myself here. No, I didn't. No, I'm sorry, this is fine. I'm looking at the next slide here. I'm cheating on you guys. The tennis ball thrown on the top of the photosphere will, if you throw a bunch of them there and they begin to have a sort of a billiard game at the top on that horizontal surface of the photosphere, if one of the tennis balls goes too far to the left, that is to say between the axis and point A, it'll roll off down the hill with increasing velocity. Same thing if one gets bounced over beyond point B. Can you see point B there? And gets onto that ski jump that I've labeled the chromosphere, it will accelerate off to the right. The second plot, the middle plot there, if you can read it, it's the axis says the outward electrical field, which is force per unit charge, labeled in volts per meter. So the electric field, for those of you who have had any physics, is the negative of the gradient of the voltage. Well, what do I mean by that? Well, look at the voltage, and if it's sloping, if it's going down, that's a negative slope, like in the chromosphere. That means that the electric field to produce that is positive. It's the negative of what the slope does. So let's say if you start at the vertical axis of the upper plot, you can see that the voltage is increasing as you move from the axis to point A. So the voltage in the middle of the tuft is the highest voltage that you're going to see in this whole area. And to get up there, to get that positive slope on the voltage, the electric field is negative. Now, it's more negative right at the axis because the voltage curve is steepest there. I don't know, if you don't follow me, don't worry about it. If you do, you see what I'm talking about. At the top of the photosphere, where the voltage curve is flat, there is no electric field. There is no force on the tennis ball pushing him one way or the other. But if the tennis ball, i.e. the positive charge, gets over beyond point B, there's a positive electric field, and that will tend to accelerate it toward the right. The bottom curve is nothing but the resulting velocity. So clearly, once you get, think of all three plots, if you get to point B and slightly to the right of point B, the force is positive. Outward force is positive. The electric field is positive and getting bigger, and the force is maximum where the slope is steepest. The skier is accelerating most rapidly at the steepest part of the ski jump. And so the velocity, the bottom curve, is continuing to increase. The increase in velocity, the acceleration, is maximum at point C. Once you get beyond point D, there's no more force on the skier, the tennis ball, or the positive ion. And so the velocity is constant. But it's moving, it's fast. instead of talking about analogies, let me say it straight out. A positive ion is accelerated by a voltage drop. The higher the voltage drop, the higher the resulting velocity. It's like saying if you drop a rock from a height, if you drop it from 1 foot, it'll get to a certain velocity when it hits the floor. If you drop it from 10 feet, it's going faster. Okay? That's all it is. The red marking there on the lower curve just talks about the region of turbulence. And that is, as this stream of ions goes out into the lower corona, there are some collisions. Collisions mean, that's what temperature is, right? Most people, I think the average person at least, has a very poor idea about what temperature is. I know it's hot outside, but what is it? It's a measure of the vibration of the atoms in the stuff that you're talking about the temperature of. What's the temperature in space? There is no temperature in space unless you're in a cloud of stuff. You have to talk about the temperature of whatever it is you're dealing with. Lastly, in the central curve there, the electric field curve, you'll see there's some blue areas and some salmon-colored areas. This is strictly from Maxwell's equations. If you're going to have an increasing electric field, doesn't make any difference what the sign of the electric field is. If it's negative or positive, it makes no difference. If the electric field is increasing, you're in a region of plus charge. And you can see that's what happens there right next to the vertical axis in the middle plot. So that's the positive charge layer. Where the photosphere, the voltage is not changing, there is no electric field, so there is no charge. And the little triangle out around between points B, C, and D, the electric field is at first increasing and then decreasing. Always in the same direction, the outward force is still positive outward, but that force is increasing for a while and then decreasing for a while back to zero. That's the famous double layer. You're going to hear people in here talk about double layers. Hannes Alfvén was famous for double layers. Irving Langmuir got the Nobel Prize for his work with double layers. That's a double layer. That's all it is. That is what it is. Why don't those positive charges and negative charges come together and neutralize each other? Why do they stay separate? Irving Langmuir found out, and that's why he got the Nobel Prize. There has to be a continual current through that double layer in order to keep it stable. And the reason that the spicules fountain those electrons up through the chromosphere is so that they can come back and satisfy Langmuir's requirement that that double layer has to have electrons and positive ions. So it all seems to work. Langmuir's work, the double layer, Hannes Alfvén's work, and now Juergen's work all works the way it does, and it all correlates. Anyway, I'd like to show you this, courtesy of Monty, this short video clip. The first thing you're going to see is a set of anode tufts under very low current excitation, and then the current's going to increase in strength, and the plasma tufts are going to go into the arc mode. You will see the photosphere. There they are. They don't like each other. It's like a bunch of kabuki warriors pushing each other away. They're all positive, and they're all looking for advantage and not finding it. You might hear Monty's voice in the background if they have the audio on. He's increased the current. The tufts have begun to go into, I know whether it's a high glow mode or that's arc mode. You can see now, it's a better model that you can see the sunspots. Sunspots are where there are no tufts. There's something that he's got the excitation such that it looks like the chromosphere. That little black thing in the bottom, I guess, Michael can tell me whether, is that the spectroscopic probe or it's a probe of some sort? There's the corona. The ring around the outside is the cathode. And of course, in the model, in the SAPPHIRE model, you need a cathode. But in real space, of course, there is, the cathode is a virtual cathode. But there's the corona. The reason that the corona there looks like it's only on one side is because the anode is closer to the cathode on that spot where you get the corona. If it were equally spaced, you'd see the corona all the way around. Sorry for the hokey ending there. That's what Stanley Kubrick used as the end of 2001, The Space Odyssey. But I really do believe that it is the beginning. Okay, down to business. There are two different types of solar wind. In this diagram, it looks complicated as all get out, but it's not. It's very simple. Forget the nice picture of the sun. It's there for eyewash. This is a radial graph. The farther out you get from the center, it talks about the velocity of the solar wind. So you can see that at latitudes, higher than 30 or so degrees, and actually lower than negative 30 degrees, the maximum velocity of the solar wind is somewhere around 800 kilometers per second. Maybe here it's more like 600. They say it's about 800. In the equatorial plane of the sun, you notice that the diagram sort of collapses. The maximum speed of the solar wind is low. It's about 400. This is a picture, obviously, you look at the upper left, from Ulysses, the Ulysses probe. SWOOPS, S-W-O-O-P-S, stands for Solar Wind Observation Over the Poles of the Sun. You kidding? They didn't get over the poles. You see the diagram stops. They don't know what's going on up there. But they did get to about 85 degrees or so. But Ulysses, when it got to 85 degrees, it was way out beyond Jupiter. So this is not a close-in measurement. And the plot here is what they measure at about 1 astronomical unit, which is where we are. Apropos what Ben was saying, the upper half of this is sort of tinged in red, and the lower half is tinged in blue. And you notice on the lower left it says the outward IMF, outward interplanetary magnetic field, is coming from the north at this point in time, and then back into the southern hemisphere. But that's from NASA. Anyway, the fast solar wind comes from normal regions from higher solar latitudes. Now this is where we begin to divide into two different kinds of solar winds. A fast wind is one that comes from not in the equatorial region, and it gets up to about 800 kilometers per second. It comes from normal regions. That is, say, it comes out of the tops of the photospheric tufts, out of the anode tufts. The slow solar wind comes from active regions on the sun's surface. In other words, sunspots. Sunspots mainly are they wander all over the place, but they're very often generally in the, what would you say, the tropical zone of the sun, near the equator. So just to state it succinctly, the fast solar wind emanates from regions in the sun where there are no sunspots, generally at more than 20 degrees latitude, and it comes out of the tops of the photospheric tufts. It approaches 800 kilometers per second, and it gets to that maximum at about 9 radii. It's not too far out. They used to think it accelerated beyond Jupiter. It doesn't, not too much anyway. Another interesting thing is it's less dense. It carries fewer ions than the slow solar wind. So it goes faster, but it's less dense. It carries less stuff. The question is why? Well, I would suggest this is the reason why. There's that first voltage curve again. And the purple is an area where there are excited ions trying to leave the sun. Sun, remember, is positive. Positive ions don't like that, so I'm out of here. It's kind of like the cross-section of a dam at the end of a reservoir. The reservoir is the purple area in the upper left. And so I think you can visualize that if the most excitable, the most excited, the most energetic positive ion in that distance, in that close to the surface area, is just higher than the voltage of the photospheric tuft, some of those positive ions can trickle over the top of the dam, if you will, and get accelerated down through the corona, down through the chromosphere into the lower corona. It's sort of reasonable that there wouldn't be too much density in that. Not too many of these guys are able to make it over the top. So although they drop far, and they're going like crazy when they hit the bottom, there are not too many of them, because not many of them are able to get over the top of the tuft. So that's the reason why the fast solar wind is fast, but it's less dense. At least that's what the Juergens model says. There's a sort of an analogy. That's Hoover Dam, or that's one of the associated dams with Hoover Dam up the road here. A high velocity, low density flow. The water, not much water gets over the dam there. Even less would get over if you raised that wall a little bit. And that's my solar transistor model. This is kind of like the emitter, the base, and the collector of a PNP transistor. If you raise the voltage in the base, you cut off the current. So, again, the velocity is high, but the density is low. There is some turbulence at the bottom, but it's intentional in this hydraulic analogy. You can see they put rocks along the bottom. They're trying to aerate the water before it gets past. If you take those rocks away and make that a nice, smooth concrete surface, there wouldn't be any, or they would minimize the turbulence anyway. How about the slow solar wind? It emanates from the equatorial region, mainly from sunspots. The maximum velocity is about 400 kilometers per second. And the ion density is more than 3 times denser than the fast solar wind. Okay, so the slow solar wind is slow, but it's got a lot of stuff in it. My thought analysis, my memory crutch on this is that the fast solar wind is like a sports car. It goes like hell, but it doesn't have much space for the groceries. The slow solar wind is like a dump truck. It goes slowly, but boy, can it carry stuff. So the ion density is more than 3 times denser than the fast solar wind. So again, the question is why? Well, is there an analogy for this one? Well, remember we said that the slow solar wind emanates from regions where there are lots of sunspots. What's a sunspot? Sunspot is a place where there aren't any tufts. The dam's gone. Somebody put a hole in the dike, and there's nothing to prevent the water. I used I'll show you a slide in a minute that I tried to show the hydraulic analogy of the slow solar wind, and I chose a bad one. The real analogy for the slow solar wind, and if I had done it right, I would have gotten a photograph of the Mississippi River right after Hurricane Katrina busted the dike. So the water in the Mississippi isn't much higher. It's 8 feet or so higher than the ground outside, and when you break the dike, the voltage drop, the hydrostatic head, if you wish, is not very high. So there's no really high velocity, but when that dike breaks, whoa, is there a flow. So it's, again, the slow solar wind is a region of high density, low velocity flow. It's like a broken dike. Anyway, that's another movie. And I've heard people decry that that can't happen. What you're seeing, don't believe your lying eyes. Believe me, I'm going to tell you what happened. No, that's what really happens. And that's a picture of what the penumbral filaments look like. And it's kind of interesting that I maintain, and you think of it yourself, the umbra is a place where there aren't any tufts. So if you look at a cross-section of this thing, you can see tufts. They're all pushing on each other. The samurai warriors, they don't like each other. But when it comes to the edge of the place where there aren't any tufts, these guys don't have anything to hold them back. So they fall in. And you can see that's happening. The reason I say you can see it happening is concentrate on the circular ring right on the outside of the penumbra, right between the yellow and the, ochre-colored areas. And you can see that the regular tufts, the yellow area, right near where the tufts are breaking away, are going outward. You see that? And the tufts in the penumbra are going inward. Sure, they hate each other. They're both positive groups of positive charge. They're elbowing each other. And so when the group that is not being held back by anything and just falls off, when it starts to flow, to move, it's still pushing on the other guys. The space is opening up, and so some fall in and some fall away. So I think that is proof, the fact that the yellow ones actually move outward while the other ones are moving inward. When space opens up for them to be able to move, shows that what you're seeing is an electric reaction. It's not a gravitational reaction. At least I maintain it's not. The analogy, of course, is the calving of icebergs. You get a glacier, and you got the ocean or wherever that water is out there, and these things eventually break loose and fall in. In this case, this guy that's falling, in the process of falling in, is not pushing on anything. So there's no tendency for the tufts, if you will, the potential icebergs that are in the wall of the glacier, there's no tendency for them to move away because nothing's pushing on them. Only gravity is pulling the one down that's falling in. This is not the case, so this is a partial analogy. It is sort of like, makes you think about what is happening on the sun, but on the sun, this guy that's falling is pushing back like crazy on the one that he just came away from, and he's moving back. Here's again that picture, and this is what I claim is happening. Just look at the red dotted line there for a second. The voltage, V2, the higher voltage, is the voltage of the photospheric tuft. V1 is the voltage of the umbra. And ions in the umbra look up and they don't see anything. They just, that's outer space out there. That's the corona. So they tend to fall along that dotted path. The dashed red curve is a voltage profile taken up through an umbra. And how many of them are there? Zillions, because there's a lot of positive ions inside the sun that love to get out. And the only reason they can't all get out is because in a lot of areas, the photospheric granules, that the dam, stops them. But at an umbra, there is no dam wall. That's DAM. So they flood out voluminously, but they don't fall from such a high height. They fall from V1 out to the low voltage of the corona. Whereas the fast solar wind ions that come over the top, they leak over the top of the dam and go all the way down the front of it, they fall from voltage V2. So the fast solar wind comes over the top of the dam, screams down that chromosphere ski jump, if you will, and fly out the bottom. The slow solar wind, many more of them, because they don't have to just trickle over the top. They just go. So the slow solar wind has a lot of ions in it, but they're not going as fast because they don't drop as far. There's a side view of a sunspot. What you're seeing, of course, if you listen to mainstream astronomers, they'll say, well, that's the magnetic field. That's not the magnetic field, that's plasma. You don't see magnetic fields. Magnetic fields are invisible. So are electric fields. They're invisible too. But plasma, no, you can see that. And so you're seeing there the side view of a sunspot, and the plasma is pouring up out of that sunspot. Over on the edge, on the lower right, that's a normal Tufts area. Stuff is still coming out, but much less of it. So that's the reason why there's the voluminous slow solar wind and the very fast, but not very voluminous, fast solar wind. There's a slide I wish I didn't put in there. I should have shown a picture of a broken dike. This is an interesting thing. This is the Reversing Falls. I think it's a national monument. Does anybody know where it is? I think it's up in Montana or maybe Idaho, I'm not sure. But this is it's not a man-made thing, it's a natural thing. It's the Reversing Falls, and it converts a fraction of, or all of the kinetic energy that's coming down from the upper left into potential energy. In other words, it's coming down from the upper left is a rather large volume of water. When it hits the stagnant, stable, placid pond into which this thing flows, there's a collision of those atoms of water, and there's a turbulence. The electrical analogy, of course, is that you've got a high current coming down, hitting a place where there are static ions, and there's a collision, and the kinetic energy is turned back into potential energy, higher voltage. And so what you get, the electrical analogy of that turbulent high bunch of water, is a concentration of positive ions right at the bottom of the ski jump. A concentration of positive ions is a good place for an E field to begin. And that E field, I claim, is what accelerates the solar wind. Here's a sort of a wrap-up slide that shows it all. You can see the photosphere, you can see the sunspots there to the center or to the right of center. And then coming out of that is a tremendous flow of slow solar wind. At the chromosphere, there's the collisions with the stable static ions in the chromosphere, and in the corona even more so. To the left, so the middle left of the corona, you see one of the famous coronal holes. Coronal holes, ooh, mystery. There's nothing mysterious about a coronal hole at all. It's just above one of the normal places on the photosphere. A coronal hole is not where there's sunspots. That's all it really is. And so what comes out of the coronal hole? The fast solar wind. Sure, where's it coming from? It's coming from the tufts in the photosphere. So it all makes sense. I sound trite. It's elegantly simple. I have to put this in because I think it really says what I'd like to say. This is by R.R. Grail. He's a very well-known, or was a very well-known solar astronomer. He said, our results in measuring the solar wind indicate that the acceleration of the solar wind is almost complete by 10 solar radii, much closer to the sun than had been expected. Okay, good. This suggests that the acceleration of the solar wind and the heating of the solar corona occur in essentially the same region, and thus that the underlying mechanisms may be strongly linked. They're not strongly linked. It's the same thing. It's the same mechanism. There's only one mechanism, and that's what does it. Juergens' model says it all. And all of these properties of the fast solar wind, the slow solar wind, the densities are all explained by, okay, one sort of just, I wouldn't call it a technical slide, but it's the statistics. What do they say? Statistics don't lie, but statisticians do. Here's the statistics, so they don't lie. The two columns are one for the solar wind and one for the fast solar wind. The first line is the flow speed, and you're talking about the velocity of protons, VP. And so the slow solar wind, the highest is around 400 kilometers per second. The fast solar wind is about 800. I hope you guys in the back can read this. The proton density, however, in the slow solar wind is 10.7 per cubic centimeter. In the fast solar wind, it's 3. So the fast solar wind contains 1/3 less than the slow solar wind. The proton temperature is, if you go down there, it's 2.3 times 10 to the 5th. It looks like you're comparing 2.3 to 3.4, but you're not. 3.4 is multiplied by 10 to the 4th, so it's kind of like comparing 3.4 to 23. Okay? So the fast solar wind, the proton temperature is much higher than the slow solar wind. Why? Because it's been through the mixmaster. It's been through the ski jump. Then look at, and this will be the last thing I'll look at this page on, for the electron temperature, it's just the opposite. The electron temperature is 1.3 in the solar wind and 1 in the fast wind. So the electrons don't take part in this. Why? Because the electrons don't go over the hill, they don't get, that hill is a hill only for positive ions. If you want to know what happens to electrons, you have to take that cross-section of the dam and turn it upside down. If you turn it upside down, it looks like a saucepan. So if electrons are coming into the sun from the lower corona, they collect in the saucepan. What's the saucepan? It's the photospheric tuft. So the electrons come pouring in, happy as larks, because they're coming downhill. Yay, here we are, we're going to collect in the pan. And they build up and build up more and more electrons, and finally, what do? They neutralize the positive charges, and they kill the photospheric tuft. That's where the photospheric tufts disappear. They fill up with incoming electrons. Anyway, there's more I can say about that, but I won't. I'm out of time here. The only quantitatively determined force capable of achieving a fast solar wind acceleration is the electric force. And I did some work on this. I won't bore you with the mathematics, but I simply would say that my final result is step 3 there. I've derived the electric field strength necessary to accelerate the fast solar wind to 800 kilometers per second. All sorts of people have tried to do that and have failed to come up with a mechanism. Remember, the corona is a non-collisional corona. It's non-collisional plasma. They don't bounce off each other. They just increase in velocity. And if you put a positive ion in an electric field, it'll do just that. Well, how strong does the electric field have to be? There's the answer. Less than 0.7 of a microvolt per meter at a distance of about 3 solar radii at the end of the corona. 0.7 of a microvolt per meter. Monty, that's your next job. Find out whether or not a glow mode plasma can support an electric field of 0.7 of a microvolt per meter. If it can, that's the answer. Okay. There's the advertisement. That's my website. If you go to electriccosmos.org, you'll get that. The stuff in white at the lower right hand is they're clickable links. And if you're interested in the gory details of the mathematics involved in both. The first one is the Birkeland current thing that I presented last year. The second one is the solar surface transistor action that says what happens if you raise or lower the dam, and can you curtail the fast solar wind? Yeah, you can cut it off. Just like you can cut off a transistor. The solar wind stopped for 2 days, back about 6 or 8 years ago. The third one is what I'm talking about now, the solar wind acceleration. So anyway, I won't bore you further. Juergens' electric sun model explains why the plasma corona exists and explains the temperature profile. And I submit that what I've just told you, the photospheric tufts are variable electrical barriers for positive ions attempting to escape from the sun. And it explains why there are 2 very different solar winds, one fast and one slow. Why the fast wind is faster and the slow wind is slower. Why the electron temperature is the same in both. Because the electrons don't go through that process. They're just there. And besides, on the average, they're coming in. Not that some don't leave, they do. But they're not affected by the shoot-to-shoot and the ski jump and all the rest of that stuff that the positive ions are. And it explains why tufts go away, because they fill up full of electrons, and why the fast solar wind comes out of coronal holes, and the stretching of sunspot penumbra is electrical. Anyway, I think only the electric sun model can explain this. Thank you.